from wherever you are around the world. Welcome and thank you for joining us. Today we're going to be discussing quantum entanglement, the God effect as some call it, as well as teleportation. With me today is Mr. Brian Clegg. He holds a physics degree from Cambridge. He is a science author and written over 20 books on the matter. Let's welcome to the circle Mr. Clegg.
Hello there.
How are you, sir?
I'm fine, thanks.
Well, this is an interesting topic. I call these my head hurters because this is kind of a hard one to understand. Quantum entanglement. I tried to look for a word that simplified that, and I couldn't find it. But I liked your idea. I think you call it the God effect?
Well, that's right, because Leon Lederman referred to the God particle when he was talking about the Higgs boson. And the idea is that entanglement is involved just as fundamentally in the way everything works together as is that particle. So I just guessed it. It was a good way to refer to it.
Mr. Clegg has written the book, The God Effect. You can see it right here. His most recent book is The Final Frontier, which we'll touch a little bit upon at the end of the show. I want to get back to quantum entanglement, and let's see if we can untangle this mystery. So, Mr. Clegg, what is quantum entanglement?
It's an effect you get with very small particles, so things like photons of light, electrons, atoms. And there's a way, essentially, they can become linked together. This entanglement is a way that two or more particles can become linked together as if they are one thing. And when they get in that state, you can separate them as far as you like, opposite sides of the universe, and a change in one particle is reflected instantly in the other, however far away it is.
No matter what the distance is?
Yeah, I mean,
wow.
The only qualifying thing is it's quite difficult to keep them in that state. So in practice, it's pretty difficult to get them the other side of the universe. But in principle, however far apart they are, a change in one instantly reflects in the other.
So now, is there a specific, is it a photon that you're doing this with?
It will work in principle with any quantum particle. So it's been done with photons, electrons, atoms, any of the very small particles that make up everything around us.
And I was thinking about something else. Does time take a play in here? I mean, does it affect, does it wear off, for instance, if you do that and 10 days down the line, does it lose that kind of ability, or does it always maintain the ability to communicate in a sense?
It's very difficult to keep particles in this state because what you need to do is stop them interacting with things around them. As soon as they start interacting with other things around them, they lose the connections. You've got to keep them isolated. And that's the difficult part of it. And at the moment, it's typically only stayed in place for a few seconds as the maximum length of time. But so in principle, you could do it to any distance, to any time. The difficulty is isolating those particles and keeping them from interacting with the world around them.
Now that kind of puts a little damper on some of my other questions, but maybe you'll be able to resurrect me here. So I know in your book you mentioned some of the current technology that might be using quantum entanglement. What are some of the things they're trying to use it for? Has it been successful at all? Is there hope for this?
Well, when you first hear of it, the thing you might think of is using it for an instant transmission, that you could send a message over any distance instantly. That's the one thing you definitely can't do.
Cannot do that.
The limitations in the way it works, essentially, because what it's sending is a random thing. You can't control what it sends. So it's basically down to the nature of quantum physics that it's probabilistic. So, for instance, if I've got two particles, they have a property called spin. And the particle here is, say, got a 50-50 chance that the spin is up or down. I look at it, and at that point, it will become either spin up or spin down. And at that exact instant, wherever its entangled twin is, it will become the opposite. So I get the communication from one to the other, but I just can't control what it is that it communicates. So that's bad if you think in terms of sending a message, but it's actually great if you want to do encryption, because what this is doing is generating a random code that nobody can ever guess what it's going to be, and nobody can intercept, because it doesn't actually travel by radio or anything like that. It actually is linked from one end to the other. So it makes it possible, this is the first thing you can do with it, to have unbreakable encryption.
So is it possible, I mean, or you think it's possible, I'm going to send you an encrypted message, and we'll just say, hello, this is my incredible encryption here. as it goes over there, are we able to find out what it's going to do to it? Let's say the letter H, as it goes over there to the other photon. I mean, or the quantum particle, can we actually determine what it's going to turn out to be, or control what it's going to turn out to be?
Well, the way to get unbreakable encryption is actually to make the encryption random. If you like, you imagine you add a number to the letter to change it to a different letter. If you can make that number totally random, nobody can predict what's going to happen. And this is totally random. So basically what we do is generate the key from the quantum encryption, the thing that makes the code. And the key's already at the other end because you've got that instant communication from one side to the other. And that means that when the message arrives in its scrambled form, I can unscramble it with my key that I've got from the encryption, from the quantum entanglement, but nobody else can access that.
Wow. How possible is this?
That's been demonstrated pretty effectively. It was originally done in Vienna, and they actually sent a message, I think it was about 5 miles across Vienna, to a bank, just as a demonstration, and made a transaction that way. And people are looking into now being able to do this from the Earth to a satellite, because once you can go Earth, satellite, Earth with it, then you can do that pretty well to anywhere, from one part of the world to another and encrypt that. And that's definitely going to be part of the future.
So let me see if I can put my head around this and maybe help myself here. What are the logistics here? What's it traveling? What kind of highway is this thing going in?
Well, we're talking here about photons. So you're talking radio or a laser, perfectly ordinary type of transmission in terms of the carrier, the thing that's carrying it. But the fact is the thing it's sending, excuse me, what you effectively do is send one half of your pair to the other end. So I've got one, you've got one somewhere else in the world. We've sent it via the satellite. I use that to encrypt my information. You use your end to de-encrypt.
Since it's going on this, go ahead.
I was just going to say you need obviously one particle for each bit of your transmission. So essentially you send a stream of particles that form the key at my end and the key at your end to unlock it.
So if I send you a message, is it then it's possible to be intercepted, but maybe not decoded?
Yeah, because once the message is encrypted using a totally random set of a key that's totally random, it is unbreakable. That's been around actually since the First World War. Something called a one-time pad. Just by literally writing it down, if you add a random value and the person at the other end knows what it is, you've got an unbreakable code. But the problem is getting the pad to the other end without secret agents intercepting it. You've got to get the actual key from one end to the other. And the clever thing about this is the key never actually travels from one place to the other. It's literally just the entanglement between this end and this end that gets the key from here to here. And because we don't care what the information actually is, we want it to be random, it doesn't matter that we can't control it.
Fascinating. Fascinating. What else is quantum entanglement being used for out there?
Well, the other big application, I guess, is teleportation, which I have to confess sounds slightly more exciting than it really is. The reason I say that is, in principle, yes, this is something that could do your Star Trek transporter, beam me down. But the problem with that is that it's going to work an atom at a time. Now, there are so many atoms in a human body that if, say, it could process a billion atoms a second, it would still take millions and millions of years to transfer a whole body. The other problem with actually going through a transporter, if we ever built one, is technically speaking, what it's doing is stripping you down to your atoms, making a perfect copy at the other end and putting them back together again. So you will actually disintegrate here, and a perfect copy of you down to your thoughts, memories, everything will appear at the other end. And I'm not sure I would like to travel that way.
Because you hope you come back.
That's not going to happen, but we can use that very small scale effect very usefully in another quantum technology that's going to be really big, and that's quantum computing.
Quantum computing.
Yeah.
Before we leave teleportation, I wonder who's going to be the first volunteer on that one.
Hello, my name's Matt, and I'm an addict.
My mom was addicted to prescription pills when I was very young, before I even turned 1.
Are you or someone you know struggling with alcohol or drug addiction? Has everyone given up on you or your loved one? The caring staff at Elite Care understands and treats you as a whole person. We offer individual and group therapy, holistic healing such as yoga, nutrition, and spirituality, medication management, and PTSD treatment. By building upon your strengths and rebuilding broken bonds, we help you begin a successful life. With our staff of licensed psychotherapists and doctors, you can be assured of the highest level of care. Elite Care is the best option for long-term rehabilitation from drugs and alcohol. Contact 888-511-0607 for more information.
Quantum computing. So what's that? What do we see there?
Well, we're hitting a limit, or we're coming close to a limit with conventional computers. I think since the late 60s, we've had this Moore's law idea that the number of transistors doubles about every a couple of years. So computers have got bigger and more powerful on the desktop ever since the late 60s. But the fact is, we are getting close to a limit because you can only make things smaller and smaller to a point. We're getting to the stage where the individual components inside one of those chips are so small that you're getting quantum effects starting to occur. You get much smaller, and you're actually going to get down to a scale where you just can't go any smaller. You'll be using individual atoms to represent things, and there's nowhere smaller to go. We are going to hit a limit on what we can do. So we need to look at doing things differently. And what a quantum computer does is it changes the whole idea of what you're basing your computing on. I don't know if you ever thought sort of computers really work with bits. So these are individual little things that can either be 0 or 1. It's like just like billions and billions of little switches, all of which can either be 0 or 1. And all your computer spends its time doing is flipping those switches, reading what they are, changing them. That it all happens at this sort of binary level inside a computer. Now, what a quantum computer does is instead of using just a little switch that can be 0 or 1, it actually uses an individual atom or a photon of light, so basically a quantum particle, as the bit. It's something called a qubit. It's a quantum bit. And the interesting thing about that is it can be in more than one state at a time. So quantum particles can essentially be in what's called a superposition. So remember, I mentioned the idea of a particle to have a property called its spin, and that can either be up or down. Before we look at it, it's actually both up and down at the same time. It's a 50% up, 50% down combined in one. It's not, it might be one or the other. It literally is both happening at the same time.
It's like bipolar.
Yeah, I guess so. And a quantum bit is a bit like that. So it effectively can be in two states at once. And as you start multiplying up the computer with more and more bits, that increased effect basically multiplies up. So it becomes more and more powerful to the extent that a quantum computer with maybe 256 qubits, so very tiny, could do calculations that a desktop computer with billions of qubits, billions of ordinary bits couldn't do.
Wow,
it makes it
really?
extremely powerful. These things are difficult to get working. There are hundreds of people all around the world working on these because they would be so effective. And one of the essentials to make them work is this quantum entanglement, because it's actually very difficult to get information in or out of them. The problem with quantum devices is always, as soon as you interact with something, you change it. So you have to keep it isolated from the world. But the nice thing about quantum entanglement is you can keep something isolated and still interact with it, because these two totally separate things can interact with each other. So pretty well all the designs of quantum computers have some form of entanglement involved in getting information in and out of them.
That's a big, big change in the world of computers.
It is. And in fact, even long before these things could be built, we are now starting to see very small ones actually being built. But long before they could be built, they'd already written two types of program that could only run on these computers. One of them is quite interesting. It's usually called this sort of needle in the haystack program, because what it lets you do is search for things much more effectively. This is why Google's very interested in quantum computers, because the sort of search where, imagine you've got a box and it's got 1 million drawers in it, and you're trying to find which drawer something specific is in. Now, if you just did this normally, you'd basically have to go through the drawers, And on average, you'd have to go through 500,000 drawers before you found the thing you're looking for. Now, what this quantum computing thing lets you do is take basically the square root of the number of operations. So the maximum it would ever take is just 1,000 goes to find that thing. So basically, it reduces the number of operations you have to do by the square root. 1,000,000 becomes 1,000. So that's vastly quicker.
Wow. Yeah, that's significant. How long do you think it will take for that kind of a product to eventually hit, if it's even measurable in time, but how long do you think that would be able to hit into the public world? I know the military probably already has it, but how long does it take to the public world?
It's mostly obviously in universities at the moment. I think we're looking at a sort of 15, 20-year timescale before we're going to have something that is pretty well a sort of, buy it and run it. At the moment, it all has to be very carefully controlled. It has to be kept at very low temperatures. So there's a lot of work to do, but in principle, that's going to make a huge change. And the other program that's already been written is in some ways even more interesting, although it's kind of scary, because what it enables you to do is break the standard encryption that's used on the internet. So whenever, say, you log into your bank, you get this little padlock symbol on your browser to tell you that it's secure. And that's using a mechanism called RSA that is a very strong way of skewering information. And what it relies on is multiplying together two huge numbers. And it's very difficult from the result to work out what those original two were. And it's all based around that. And this particular algorithm is basically designed to find which two numbers will multiply together to make a very huge number. And it can do things basically vastly quicker than any computer could ever do. Because of that, it's kind of scary too.
Yeah, it would be very scary, especially in today's era. Yeah, there's a lot of hacking going on out there, unfortunately. We have a few minutes left, and we got a couple topics I want to cover really quickly here. Just to be clear for myself, maybe you can give me a brief response on this. You said that the quantum particles have different spins up and down. If I remember correctly, there were different versions of those as well, going from different angles.
Yeah, well, essentially, I had gave you a simple case where it's, say, 50% up, 50% down are the probabilities, but it can be anything in between. Okay. So you can have something that's, say, 13.7% chance of being up and the remainder a chance of being down. And what that's the equivalent of, if you think of it as like sort of an arrow that is pointing so much up and so much down, so it goes round as you get more. So 50-50 would be like that. That will be all up, that will be all down. You can actually position that arrow at any point. So effectively what you can do is put a real number in there. At the moment, a computer has to work with integers, with ordinary numbers, and really it starts approximating whenever it deals with a real number. So if you think something like pi, that a number that goes on forever, a computer can only ever approximate to that. But what one of these could do is actually specify an exact number between 0 and 1, say, down to every decimal place. So effectively it's an infinitely long number, which gives you the potential, obviously, for a huge amount of accuracy in calculations.
Well, we got a couple of minutes left here. We got a fastball question, but before we get to the fastball question, on your latest book, The Final Frontier, I know you were talking about us going into space and exploring it, but you had a little different take on it. I remember we talked off camera. You said space travel may not really be science. Is that what you're saying?
I think so. I think the problems we have with space travel are mostly because we tend to lump it in with a science budget. And scientists don't like that because, frankly, you don't get a lot of science bang for buck when you're up in space. Something like the International Space Station is a very expensive way of doing an experiment. They'd much rather be doing something with a collider on the ground or something like that than they would be putting a lot of money into a very small experiment in space. And arguably, space has never really been about science. When we went to the moon, it was very much about the political race between the USA and the USSR. And in the future, I would suggest it's really about human beings doing what they do best, which is exploring, finding out. It's almost more a political thing than it is a scientific thing. It's more about spirit than it is about doing scientific experiments. And I think we've got to see it as that. You can always say it should be in the defense budget because it's about defending the way we are as human beings. It's about our future as human beings. It gives us a frontier. This final frontier, yes, it's quite fun because it comes from Star Trek. The fact is, it is genuinely the frontier. Once we had that in North America, that's gone as a frontier. But that one is out there still. And it's that challenge. It's that same challenge that took people across America, I think, that we ought to be looking for, rather than saying, oh, how much are we spending on the science?
I want to take you back to quantum entanglement for a second before we get to your fastball question, which is coming right after it. They're kind of related. I can't remember. I read this, and it was talking about quantum entanglement being used to maybe travel into time somehow, or communicate in the past or in the future. What's going on there?
Okay, well, in a way, this comes more into another book I wrote, which is How to Build a Time Machine, because it is possible to travel in time. That's the starting point. There's nothing physically, no physical problem with traveling in time. There are practical problems with no physical problem. Really, all you've got to do is move. And the faster you move, the more you'll travel in time. That's something that relativity tells us. And if we can get a spaceship traveling out at very high speed for a number of years, its time will be significantly different from the time on the Earth. The thing we've had going furthest so far is Voyager 1, and that's gone about 1.1 seconds into the future. That's actually traveled in time about 1.1 seconds in the time it's been travelling. If you could get something much faster, you can imagine it going several years into the future. And if there's some way you could use entanglement to send a message, as I say, as yet, we can't think of any way to do this, but if there is some way, you could get an instant message from us to the spaceship. So effectively, that message has traveled through time because it's left here and instantly arrived at the spaceship, which is in our future. And so it's really just a way that if you could combine time travel, a time-traveling object, with instant communication, then you can send messages backwards in time in principle, because basically it's coming back from the future, as it were. It's coming back to an earlier point from the future. It's one of those things where you need a picture to understand it, I think.
Yeah, we really do. So I could, technically, if we ever figure it out, I could actually send a message to Abraham Lincoln and say, watch out?
Unfortunately, no, because all the ways we know to build a time machine won't go back before the time machine was first constructed. It is, in principle, possible to create a time machine, although going into the future is much easier than going into the past. But effectively what they do is slow time down in various ways, or speed it up in various ways. So you can get back to the point where you started from, if you like, but you can't get back past it. Somebody has to have built a time machine before you can get back to the point where it was first constructed.
H.G. Wells didn't have that problem. All right, well, here's your fastball question. You ready, sir?
Yes, indeed.
Where would Mr. Clegg like to be beamed up to once we figure out teleportation?
Okay, I think I would just be like, I'd be quite happy just to see Mars. I don't fancy the idea of spending, 6 months or a year on a spaceship getting out there, but I'd be very interested to visit our nearest neighbor, or our nearest semi-habitable neighbor, instantly.
There you go. There you have it. He wants to go to Mars. Thank you very much, Mr. Clegg. Once again, everybody, here are his books, The Final Frontier, The God Effect. He's got 18 more. We don't have enough space to put them all, but they're all wonderful books. I highly recommend them. These are great stuff. If you want to learn more about quantum computing, we might have to contact MI5 or MI6 or CIA. They might already have it going. Once again, thank you so much, Mr. Clegg. Thank you, everybody, for joining us. Remember, our motto is simple. Wherever there's psychology involved, even in quantum entanglement, we are there. See you next time, everyone. And also, catch our web TV show, Circle of Insight, on therapycable.com.